look at a review of limits, and hopefully this is helpful. Okay, so when you first get a limit, you should always check and just plug the number in. So for example, 9 plus 5 is 14 over 4, so that's the answer. These are no problem problems. So when we talk about problems in limits, we mean dividing by 0 or dividing by infinity. Those things create problems. Okay, then the next type of question you could get is a 0 over 0 problem. So what I mean is when you put the 3 in, you get 9 minus 9 over 3 minus 3. So we don't write this down, but what we're thinking is we got a 0 over 0 problem. That usually means that if you can factor, you can remove the problem. Because the same thing that gave you 0 on the bottom is likely what gave you 0 on the top. Not always, but we're going to check to see if that's true. So then when we cancel this out, now it becomes a no problem problem, and when we put 3 in, we get 6. So what this is saying is as x approaches 3, this whole limit notation when I say equals here means that the y value is approaching 6. So we're saying as x approaches 3, y approaches 6. Or up here, as x approaches 3, y approaches 14 over 4, or 7 over 2. Okay? Might as well reduce that. Okay, then there's problems where x is approaching infinity. So if you think about it, if x is approaching infinity, you're looking at the ends of the graph, like the arrows at the end. So we say that these are end behavior. Okay? And an easy way to solve these is because you're putting in infinity, you just think about only the biggest things are going to matter. Like infinity squared, it doesn't matter if I say plus 5 times infinity or plus 6. So just the biggest thing on the top and bottom is what's going to count. And we say this is an end behavior model. So we look at this, and then algebraically we remove the x's, and we get that this equals 1/3. And then that's the answer. So really what we're saying here is as x approaches infinity, y approaches 1/3. So we've actually described a horizontal asymptote. Okay. All right. So we can try one more here. So x is approaching infinity, so I'm just going to count the biggest thing on the top and bottom. And then I'm going to solve this limit as x approaches infinity, x cubed over x to the 4, which as long as I have x's, I have to keep the limit. So I have 1 over x. So now if you think about it, if you put infinity in, you get 1 over a really large number. It approaches 0. Okay, so you sort of want to know that limit here. So again, we're saying as x approaches infinity, y is approaching 0. So remember, the whole limit is telling you what y value you are approaching. And this is why we use the limit notation to show that it's not y equals, it's y is approaching. Okay? All right, and then we can have limits that actually equal plus or minus infinity. These are a little trickier. And they occur when you have a number over infinity. So basically, you know, when I sub 3 in here, I get 3 over 0. Now, I'm not going to write that because I can't divide by 0, but I'm thinking that. And if you think about 3, divide it by a really small number, that's going to approach infinity. Okay, so basically what we're saying is as x approaches 3, y is approaching infinity. And so we're describing really a vertical asymptote at x equals 3, right? Okay, so that's a quick review of limits. I don't know how much of these you'll be asked on the exam, but at least it's a little review. The one that you really want to know is the definition of a derivative or first principles, and I would suggest this is the one you want to know. So it's no longer, this is now not a y value, it's the limit of an m value. This is slope, right? So what we're saying is as h approaches 0, slope approaches something. Okay, so it'll find us the derivative because it's slope, and it's instantaneous slope because I'm dividing by 0. All right, so I can get the derivative by plugging this f of x into the formula. So it says replace x with x plus h. So I have x plus h cubed plus 2x plus h plus 1. Okay, so there, that's me plugging f of x plus h in, and then minus, and now I'm going to just plug x in. So x cubed plus 2x plus 1, and then all over 0. So again, this is f of x plus h, and then this is f of x. Okay, so this is important to understand how that function notation works. And then you get an opportunity here to use binomial expansion. So I can do out Pascal's triangle. And because it's x plus h to the 3, I'm going to use the third line, and these will be the coefficients. And I'm going to say 1 and x cubed and 0 h's plus 3x squared and 1h plus 3 x's and 2 h's, and then plus 1 and no x's and all h's. So that's the expansion of that. And again, that's a nice review of that. And then I have plus 2x plus 2h plus 1. And then I'm going to remove the brackets and distribute that negative in, and I get minus x cubed minus 2x minus 1 and all over h. And then you should be noticing that I forgot to write limit, and I can't do that until I've let h be 0. All right, so now hopefully some things are going to cancel on the top. So my x cubed cancels. That doesn't cancel. What else? 2x and 2x, and my 1 and my 1. And then on the top, I'm going to factor out an h to cancel out with the h on the bottom. So I have 3x squared plus 3xh plus h squared plus 2. Okay, and then those h's cancel. Now I've just got rid of the thing that is the problem, the 0 over 0 part, because when I put h in, I got 0 over 0. And then I now have 3x squared plus 3xh plus h squared plus 2. And as soon as I let h be 0, and it's not a problem, which here it isn't, this will go away, that will go away, and I'll be left with 3x squared plus 2. And using our power rule, if we have f of x equals x cubed plus 2x plus 1, according to the power rule, that is 3x squared plus 2. So that checks out. Okay, hopefully that was helpful.